This is a pendulum. It swings back and forth attached to a fixed point on the ceiling up here. We're choosing to be the origin of our coordinates. And it's imagine as a point mass at the end of a rigid rod, maybe a thin metal rod or something, swinging back and forth, angle theta from vertical. And our goal is to figure out what is that angle theta as a function of time as this pendulum swings. It's actually going to turn out to be impossible to do, but we want to develop a differential equation that describes the motion, and we can approximate some things to get a good approximate solution. But we want to find that differential equation in terms of derivatives of theta with respect to time related to other features of the problem. Now, I've actually already made a video about solving this problem using Newton's laws and the standard xy coordinates that everyone learns in an introductory physics class. It was a process. It took a lot. It took the whole board and a long time and a lot of details. I want to show how using coordinates that are a bit more optimized to fit the problem can make this a simpler thing to solve at the cost of a much messier setup for Newton's laws because the coordinates are more complicated. So in particular, I want to use, instead of xy coordinates, I want to describe this system using polar coordinates in this plane. I'll show you the polar coordinates I want to use in particular. I'm going to look at coordinates. Let me just sort of sketch it over here. If we've got our x and our, well, that's not x. If we've got our x and our y, and we're looking, I'm going to follow these conventions. So, and if we're looking at a point over here somewhere, this is theta, and the distance from the origin is r. That distance, the radius from the origin in polar coordinates, then this point is specified by the r and the theta. And we can also talk about unit vectors, r hat and theta hat, in the directions of increasing r and theta at that point. So at this particular point, the r hat unit vector points outward from the origin, and the theta hat unit vector points exactly the direction this would be moving at that point if it swings in the plus theta direction. Now, these unit vectors would be different everywhere, right? If I had looked at this point, my r hat would be outward, and my theta hat would be this way. If I had looked at this point, my r hat would be outward, and my theta hat would be that way. So r hat and theta hat, their directions in space change from point to point on the plane. This is a big distinction from x hat and y hat that always point the same directions. But r hat and theta hat are, we'll see, sort of optimized for a problem like this one that has motion around a fixed origin point. So in that case, in this story, we have to pay attention to these things because if my position, you can always write down your position vector as r vector is r times r hat, the distance from the origin, and then the r hat means in the direction away from the origin. That's allowed. But then if I take the derivative with respect to time of position to find velocity, that derivative, I have to use the product rule. I'm using dot to refer to the derivative with respect to time of a quantity. So r dot here is the time derivative of r times r hat, but r hat changes as we move. We're in different positions as we move, so r hat may change. So this is r times r hat dot. You have to use the product rule to find those. What is the time derivative of r hat? Well, there are a lot of ways of coming up with this. I'm not going to go through those ways right now. The whole point of this method is to have you or someone else plug through these relationships early on, and before you start your problem, and then you're going to use those results to solve the problem later. So in fact, the result we find, r dot times r hat, plus, that matches, plus my r here is times the r hat dot. The derivative of r hat with respect to time is theta hat times theta dot, how fast theta is changing. Maybe that's plausible. If I change my position around in the theta direction, my r hat will go from here to here, and that change from here to here is in that sort of theta hat direction. So maybe that makes it plausible that r hat dot is theta dot theta hat. Maybe you just have to believe me for now. There's a lot of work that went into getting this right. There's even more work into the second derivative of position. I guess I should have written acceleration here. My acceleration vector is the second derivative of the position vector, and because now we have to take product rules of all these things, you'll find that the product rules of all these things, there are a lot of derivatives going on. You get this expression down here. It's a mess. There's an r double dot term, the second derivative of time with respect to time of distance from the origin. There's an r times theta dot squared term, both contributing to the acceleration in the r hat direction. Now, these actually make sense. R double dot is the acceleration in the r direction. This is just, acceleration, second derivative of distance. This term you might recognize as r omega squared, or v squared over r. It's the centripetal acceleration, the acceleration toward the center in circular motion. That's familiar. It's in the r hat direction because it's toward the center. So these terms both have familiar meaning. And if you go through the whole derivation, you'll also get an r theta double dot term. Theta double dot is the second derivative of angle, and if you're at a fixed radius, that just means your angular acceleration. How quickly is your angular motion accelerating? And then there's this weird term, 2 times r dot times theta dot. And that one is harder to understand intuitively. This is called the Coriolis acceleration, and it's got its whole story to go with it. Point is, you just derive this equation. Someone has derived this equation, and if we're going to use Newton's laws in polar coordinates, you start from this point. You start from this point, and then you'll say, what do Newton's laws look like? Well, Newton's second law says force equals mass times acceleration, or mass times r double dot. That's Newton's law, Newton's second law, and r double dot now has this form. This second derivative of position has this r hat and theta hat form. So I just need to find my forces on this point, on this particle, in r hat theta hat coordinates. That means I need a free body diagram. So let me draw a free body diagram for my particle and draw my forces. Force of gravity points down, and there's a tension force along the rod. That's how that's how central forces work, is that we're going to have a tension force along that rod. And now I want to write these in terms of coordinates that are in the r hat and theta hat directions along the way. So what's that look like here? Well, the r hat direction goes this way, outward that way, and the theta hat direction goes this way. Those are the directions we're using to label this. And now I see I've put my label FG in a terrible place, truly terrible place. Here's my force of gravity downward. All right, and I want to know how to label. I guess I should label my angle. The angle in the problem was labeled up here. And so I guess there are lots of things we could do. This angle is theta, and so let's see, if that angle is theta, then this angle is also theta, and we could maybe draw a parallel line down here to get ourselves a right triangle. This is all the usual sort of thing that you do. If I want to write my forces in r hat theta hat components, I can immediately see that my tension force is going to be all in the minus r hat direction. So my tension force, just for simplicity, I'm going to write this as minus t r hat, because it's in the minus r hat direction, and I'm just going to call its magnitude t to make less writing for myself. Meanwhile, my gravitational force, I have to look at these pieces. My theta I have identified down there in the graph. Make sure that's right. Yeah, it looks plausible. Okay, good. So this is good. That's my angle theta. And what's that tell me? I guess my force of gravity, the magnitude is mg. My r hat component is positive, and the magnitude is mg, and that is adjacent to my angle. So this is mg cosine theta, because cosine is adjacent over hypotenuse, and that's in my r hat direction, because it's that gravity is pulling us outward from the middle. And then for theta hat, gravity is pulling me, looks like in the minus theta hat direction is drawn here. So minus mg sine theta, theta hat. That's my force of gravity in components, in r hat, theta hat components. So I've got these pieces, my forces in those components, And now I can put those in to Newton's second law. I can put that in on the left, and on the right-hand side, I'm going to put this thing together. Let me write that out. Left-hand side says the sum of these two forces is minus tension r hat plus mg cosine theta r hat minus mg sine theta hat, and that equals, that's the left-hand side of Newton's second law, the right-hand side equals mass times this whole acceleration piece. Oh, but I can simplify my life a bit when I copy this down, because I've said this is a rod of fixed length. That means it's not getting longer or shorter. My radius, my distance from the center, is fixed, is constant. That means that r double dot is 0 and r dot is 0. Those two terms go away because there's no change in distance from the origin. So I'm left with just minus r theta dot squared times r hat plus r theta double dot times theta hat. That's my Newton's second law equation adjusted to match these polar coordinates. And now at this point, I just equate the r hat parts with the r hat parts, the theta hat parts with the theta hat parts, and I have differential equations for all these things. It turns out, the way this is set up, the tension force is only in the r hat part. I don't care what the tension force is. So I'm going to ignore the r hat components entirely. I'm just going to look at the theta hat component, which tells me, when I look at theta hat in this, I will find that, well, I've got minus mg sine of theta on the left has to equal mr theta double dot theta on the right. And I guess I should say my r on the right, the radius, the distance I am from the origin, is just the length of my rod, L. So this is ml theta double dot. So if I want a differential equation for theta, I can just solve for theta double dot in this equation, dividing both sides by ml. I'll find that theta double dot equals, well, the m's cancel, minus g divided by L times sine of theta. That minus g over L sine theta is the exact same equation that we came up with when doing Newton's laws using the xy coordinates. Here, it's kind of a mixed bag whether this is easier or harder. I think I'd say that if I have these equations for acceleration, especially, written down in polar coordinates already, if I have this in terms of r hat and theta hat already written down for me somewhere, then I am perfectly happy to use this method. And this is actually really efficient once I've done so. I've gotten to this point and gotten to this differential equation for theta in a pretty efficient way. It was just a free body diagram in tilted coordinates, basically, which I interpreted as r hat and theta hat. And I was able to set up my problem very smoothly and easily and get to this result very easily, ignoring the r hat parts where the tension was involved. This got me here. I will say, as I mentioned in the previous video, this is not solvable. There's no closed form solution for theta as a function of time to this. But if I take the limit where this is approximately, if theta is small, if I say theta is much less than 1 radian in this problem, and I say theta is small, then I have the second derivative of theta equals negative constant times theta. And once I have that equation, this is a standard harmonic oscillator problem, and I can solve it easily. My general solution there is that theta is some amplitude times, one way of writing it is cosine of omega t plus phi, where omega squared has to equal g over L. And you can check that that form, where phi is a constant, a phase offset, you can check that that form, second derivative, satisfies the approximate equation. And as long as we have small angles, as long as our angle is small, this function of time, the pendulum function of time, has this nice frequency, well, angular frequency, square root of g over L, that comes out of this result. So you can solve this problem pretty easily if you or someone else has already done the work to write down acceleration in the polar coordinate system. Obviously, that was a pain to get there. I did not even try to derive it for you just now, because the point of this method is that someone else already did it. If you have a problem that it fits polar coordinates well, like this one does, then this is remarkably useful and a very great shortcut to get to an answer quickly. If you had some other problem where polar coordinates weren't such a good fit, then this will just make your life much more painful for no gain. So there are pros and cons to this method, but it's a good one to know because it's another way of solving the pendulum, and it shows the power of having coordinates that are optimized to your system. Now, the really optimal way of doing this is using Lagrangian mechanics, and that's another video.